Welcome back to Foundations of Visualization. In this lecture, we're going to be talking about a fundamental framework for thinking about the different components and pieces of a visualization, and that framework is called the Grammar of Graphics. The Grammar of Graphics was first introduced in the 1990s by Dr. Leland Wilkinson, and the basic idea is that it gives us a common language for thinking about the ways that we make design choices in visualization. And this language is going to describe everything from the data that we use, how we divide and process that data, to the visual channels that we display on our marks, whether we use size, color, position, and how we convert data into those channels. The reason the Grammar of Graphics is so critical is that it is a foundational tool and technique underlying many of the most common packages that we have for developing and designing visualizations, including Altair, which is the subject of our next lesson. So how we talk about visualization is critical for understanding and breaking down the individual component techniques and design choices that we use both to create and to interpret visualizations. And so what we need to be able to figure out is how do we abstractly categorize the different components of a visualization. There are certain features of visualizations that are common to almost all of the common representations that you'll see. And establishing a common language for how we talk about and how we use them allows us to not only understand how to apply them in design and how to read those designs, but also enables us to start to understand and investigate what are effective choices or settings for these different variables within the space of a visualization that will best communicate the patterns that we need to see in our data. In visualization, we can describe a lot of these pieces through the grammar of graphics. Just like grammar in language, it gives us a systematic and structured way for reasoning about how we look at and how we create visualizations. The Grammar of Graphics divides the design of visualizations into 7 core components. The data, or what is it that we're choosing to show, the aesthetics, or how do we show it, the scales, how do we get from data to a visual representation, the geometric objects, what kinds of marks and what shapes of marks are we using, statistics, how do we choose to pre-process or wrangle our data, facets, how do we choose to divide our data into multiple representations, and our coordinate systems. How do we choose to position our data on the screen? The reason that we're talking about the Grammar of Graphics specifically in contrast to other ways of reasoning about visualization design is that the Grammar of Graphics underlies several common visualization toolkits, including ggplot in R, Vega Lite and D3 in JavaScript, and the subject of our next set of lessons, Altair, which is a toolkit that's developed for visualization design in Python. So what I want to do next is I want to break down this set of 4 scatter plots that we have from our last lesson. If you recall, this is Anscombe's quartet, in terms of how we reason through these visualizations using the Grammar of Graphics. So we start with data, just simply what data is being displayed. It helps to be specific when you're thinking through and reasoning about the correct ways to understand and investigate a data set, about what are the specific target dimensions or attributes you're choosing to display. In the case of Anscombe's quartet, what we have is a set of 4 data sets with 13 points each, and each of these 13 points has an X and a Y dimension. When we move to the next layer of the grammar, we have aesthetics. So what are the visual elements of our visualization? And this includes everything from the visual scaffolding that helps us interpret our data, so things like the axes, to the relative positions of points, to the encoding channels or the visual channels such as shape, size, and color that we're going to use to represent our data. So in the case of Anscombe's quartet, here we have 4 plots that are arrayed in a grid. Each of these plots has 2 axes, an X and a Y. They use position to encode value, and they use hue, whether it's purple, blue, red, green, orange, to identify what our different data sets are. Moving to the next level is our scale. So this is that idea of a mapping, which will be the subject of one of our later lessons. But how do we get from our data values to the range of values we see on the screen? So our X positions are mapped linearly from data to pixels on the range of 0 to 21. Y positions use that same mapping on a scale from 0 to 13. And the colors that we choose to use are blue, orange, red, and green to indicate our 4 different data sets. At the next level of the grammar of graphics, we'll talk about geometric objects, and this is simply what shape do our marks take? In this case, our data is represented using points or circles. That's fairly common for a scatter plot, but as we start to move into different kinds of charts, we see alternative forms of geometries. For example, we might see lines in a line graph, bars in a bar chart, or things like area in less conventional representations like tree maps. We can also think about the statistics. How is the information that we see in our visualization statistically processed prior to representing it? And this includes things like how is it grouped? How do we choose to compute these statistics? And how do we lump together different subsets of our data in meaningful ways? The statistical computations in these graphs are pretty simple. So our marks represent raw values from our data sets, but we also have these computed regression lines that provide us with a little additional statistical context as to the distribution of our data values. Moving to the next level of the grammar, we have facets. How is the data broken into its different component visualizations? Oftentimes we'll just have one single visualization that represents a certain subset of the data. But as you've probably seen in the wild, it's not uncommon for visualizations to be represented through multiple data sets or multiple visualizations. So in this case, we faceted our data according to each data set. So we have data set 1 in the upper left, 2 in the upper right, 3 in the lower left, 4 in the lower right. But data is also commonly faceted on different dimensions. For example, we might have one plot that shows dimensions x and y, and a second scatter plot that shows dimensions x and z. And you'll see examples of this throughout the course. Finally, we have our coordinate system. So this is thinking about how are our data mapped to different positions on our chart. So in the case of these scatter plots, we are mapping our data according to a Cartesian axis. But in the case of other kinds of representations, we often see things like polar coordinates, where we're mapping things to radial axes. What I'd like you to do now is pause the video for a little bit of practice. And in particular, I want you to use the grammar of graphics to try to deconstruct the bar chart on the right, which we saw in our previous lecture, according to the grammar of graphics. So here is my deconstruction of this bar chart. Yours may vary a little bit, and that's okay, but generally speaking, the data that we are seeing here is smartphone market share percentages. In other words, what company has what proportion of the market. The aesthetics that we see are our labels and our titles. Then we also have X position mapped to different categories. So each position is mapped to a specific company. We have a continuous Y position, and we have different colors for our different categories. In this case, those categories are the different companies represented in this share. In terms of our mapping scale, our X value, our market share, is mapped to a scale between 0 and 45%. Our Y scale is mapped to discrete positions along the axis, so positions 1 through 6, which with each company occupying a unique position. And our companies are also mapped to one of 6 colors, with each company mapped uniquely to one color. The geometric objects we have are bars. The statistics that are computed is just providing the raw percentages, the raw data. We don't really have any facets here. We're showing all of the data we have on one chart, and we're doing so with a Cartesian coordinate system. Everything is a pretty linear layout. So one trick here, as I mentioned, that might cause some variance is, for example, I'm assuming that the data going into this chart is pre-computed percentages, and that we have the percentages, and therefore when we show the percentages, those are raw data. However, one could envision creating this chart with the same representations, but using the dollar share, and then computing as part of the statistics the proportion of that dollar share represented by each company. So this gets to where it's really handy to know what your underlying raw data looks like in order to understand how it's being transformed into your final representation. And in terms of knowing what that data looks like and having control over those computations, in our next lesson, we are going to move into some hands-on work with a specific visualization library called Altair. And using Altair, we're going to be able to take advantage of the structures offered by the Grammar of Graphics to create powerful interactive visualizations with just a little bit of code. I look forward to working with you all then.